Okay, so we got to look at water again. So let's just look again, remind ourselves about valence electrons and how things go together. So we've got oxygen. Here's oxygen. It's got 6 valence electrons in red, and then the oxygen has space for 2 more electrons in its valence shell that are not there. It has 2 empty spaces in its valence shell, and it would like to fill those up so it gets more stable. And oh, look at these hydrogens coming in. They've got 1 extra electron, 1 electron in their outer shell, and a empty spot in their valence shell. Boy, wouldn't they like to share and join together with oxygen and make an H2O. We've seen this before. Everybody's happy. They've got full outer shells when they share their electrons. So there's our H2O. We're going to see something similar with hydrochloric acid. Here we've got chlorine. The hydrogen has 1 valence electron and has 1 extra spot there. The chlorine has 7 valence electrons, those green valence electrons, and it has 1 empty spot. The chlorine steals that electron pretty much. I mean, it's not a total ionic compound, but it pretty much steals the electron away from the hydrogen, and it fills that outer shell, and then they come together, and everybody's happy in this molecule, but it is a very polar molecule because the chlorine is stealing, pretty much is hogging that electron of the hydrogen most of the time. Okay, so hydrochloric acid is a polar molecule. Let's see what happens when it goes into water. If we take the same hydrochloric acid and we've got a water right here, that slightly negatively charged oxygen is attracted to the positively charged hydrogen. We've seen that before with those polar molecules. And the oxygen is actually sometimes able to pull that hydrogen. Well, actually, it's pretty good at this. It's able to pull the hydrogen right off of the chlorine. And we end up with this hydronium ion. And you notice it's got 3 hydrogens, H3, 3 hydrogens, and 1 oxygen. And because it just pulled the hydrogen off without pulling the electron off, notice the chlorine still has hydrogens, 1 electron. So it has a negative charge. The chlorine has a negative charge. The hydrogen has a positive charge. The overall, this whole thing, the hydronium ion has a charge of +1. And it is floating around with 3 hydrogens on 1 oxygen. And hydrochloric acid, when it is put into the water, turns the water into the hydronium ion, and this is the definition of an acid. Well, it's one definition. They get more complicated just like anything, but let's just go with the simple answer, is acids increase the number of hydronium ions in the water. So as we increase these hydronium ions, that is what is making something more acidic. Something highly acidic will have a lot more of these hydronium ions. A weakly acidic thing will have just a few of these hydronium ions. Okay, so sodium hydroxide is a base, or lye. That's the, if you watch the Fight Club one clip, that is what is cause the chemical burns and is what is made, what they use to make soap. And it is a very strong base. And here we have, what if we put a base in water? We've got sodium right here, and then hydroxide. You notice that OH, hydroxide, sodium hydroxide. And this is a ionic compound. We've got the sodium has a positive charge, the OH has a negative charge because the oxygen has stolen an electron away from the sodium. And when they get into water, they split up, and we end up with hydroxide floating around on its own and sodium floating around in the water on its own. And then we've got this water, but hey, we don't have the water actually react with the hydroxide. We just end up with bases. We just end up with a bunch more hydroxide in the water. So the definition I'll let you read that. I forgot to say that. So the hydroxide ion is what defines a base. bases increase the number of hydroxide ions. So the more of these in the water, the more basic the water is. Okay, so how basic is it? You know, and like, what does that, how many do we need in order to change the pH? And that's what we need to look at. And what happens here, so what this is, there's a lot going on here, and I recognize that. But we've seen this pH scale, we've seen the colors before, we've seen these products, but I want to point out that some of the things you might have seen before. This right here, this 3% hydrochloric acid, that is that's the acid, the hydrochloric acid that I tend to use for just about all of our experiments we used this year. It was 1 molar hydrochloric acid. It's the common amount that we use. And remember, I told you that if you spill it on yourself, you should probably go rinse your hand off because it might burn you and irritate you if you don't. But it wasn't like, oh my God, watch out, you're gonna burn your skin off immediately. So this is like, you know, and it's a little bit, it's battery acid, you know, it's strong, but it's not like dangerous strong. So that's the chemistry lab HCl. That is a pH of 0. Notice we hadn't even seen a pH of 0 before, but it does exist. And then the super concentrated stuff, the 30% hydrochloric acid that I don't even want to touch without a bunch of gear on, that is a pH of -1. Now let's look down at the other side. We've got 3% NaOH. That's a typical concentration I would use of sodium hydroxide in the lab if we ever used a base, and that would be a pH of 14. That's a strong base, but not like burn your face off immediately. You have time to rinse it off before it starts burning. But concentrated sodium hydroxide at 30%, oh man, you don't want to get anywhere near that stuff. That is a pH of 15. And now what I want you to notice is the difference between 3% sodium hydroxide and 30% sodium hydroxide is only one step in the pH. You go from 14 to 15, but it's 10 times as strong, right? 3% to 30%. That's 10 times stronger. And that's what we're seeing. I want to point out that these numbers over here, we have the hydronium ion up here, and that is at neutral, we have the same amount of hydronium ion as hydroxide ion. That's why it's neutral. There's the same amount of each of them. But as you go more acidic, if we go from a 7 to a 6, we go from the same amount of hydronium ion and hydroxide ion to 10 times more hydronium ion, 10 times more hydronium ion and 10 times less hydroxide ion. But really, we're thinking about this as we think about acids, we're really watching this hydronium ion go up by 10 times, 10 times, 10 times stronger and 10 times stronger and 10 times stronger until when you're at 0, a pH of 0, there's 10 million times more hydronium ions in it, in that hydrochloric acid, that 3% hydrochloric acid, 10 million times more than regular distilled water. And the same thing happens with bases. As you go down the pH, as you each step on the pH scale, you're going 10 times more hydroxide ions in the water, another 10 times, another 10 times, another 10 times, until when you're down at 14, a pH of 14, you have 10 million times more hydroxide ions in that water. So that is why it's stronger. And now the 30% has 100 million times more hydroxide ions in it than distilled water. So that is why they get stronger. Each one is 10 times stronger. So let's look at what that really means. When I was trying to dilute these things and make up these solutions for you so that you're not working with the crazy strong stuff, in order to get 3%, that typical lab grade hydrochloric acid, from the 30% concentrated stuff out of the crazy glass bottle, in order to make that, I had to start with 1 beaker of concentrated hydrochloric acid, and I'm wearing the full gear, you know, face mask, apron, gloves, the whole deal. I put a beaker full of that stuff, and I want to dilute it 10 times, right? I want it 10 times less strong. So I take 1 beaker of that, and I have to add 9 more beakers of water so that it's diluted 1 beaker of the strong stuff to a total of 10 beakers worth of solution. And that looks like this. We got 1 beaker of this and 9 beakers of water. It's diluted quite a bit. And that is just 1 pH step. That's going from from -1 to 0. That's that 1 pH step. So now in order to make this stuff, the, weaker, the not as, a lot more diluted, 10 times more diluted, stuff you don't even have to worry. If you spill it on yourself, not a big deal. It's pretty much, like almost like vinegar, a little bit stronger than vinegar. To make that stuff, the stuff that you're not so scary to work with in lab, from the 3% typical lab grade, I have to do that same dilution again. I have to take 1 beaker of the 3% and then add 9 beakers of water again. And that dilutes it 1 to 10 to get down to that 0.3%. And that's still only a pH step. Notice I've gone from 0, a pH of 0, to a pH of 1. And it took a dilution of 1 to 10. So now let's do one more. If I want to go from 0.3 to 3, same thing, 0.3 to 3, I need to dilute it 10 times again. Same thing. Take 1 beaker of the 0.3 of the, the orange stuff, and then, wait, it should be a little bit pink. Anyway, and then add 9 beakers of water, and I end up with this very diluted stuff. It's pretty much, it's like, as strong as lemon juice or something. I have to dilute it with 9 beakers of water again. Okay, so here's the big trick. If I want to make 0.03 hydrochloric acid from the 3%, is the lab grade, just the stuff we use in lab, to about like lemon juice, how much do I need to dilute it? That is 2 pH steps, and it's 100 times more dilute than the chem lab grade. So I'm going to let you think about that for a little bit. If I take 1 beaker of the 3%, how many beakers of water do I need to mix with that to make it 100 times more diluted, or 2 pH steps? It's 99 beakers of water. I'll just show you what that looks like. It looks like this. It's a lot of water. It's like a lot of water. So that's 99 beakers worth in order to dilute that 100 times to get it to go 2 pH steps less acidic. I think that's what I wanted to tell you. And you could study this lovely chart and see if you understand it with bases.